Swayam Prabha. Digital India. Educated India.
We're looking here is again very fundamental. I will be again very fast. I will do a course of equilibrium thermodynamics in 45 minutes. But again, the idea is to give you the PDF, and then you can see, you can have, let's say, kind of rehearsal of what you have done in the past and so on. But I think that is important because it's preparing the things for what we are saying tomorrow. So, thermodynamics. What is very important to say, to remember, is that thermodynamics, especially equilibrium thermodynamics, is starting, let's say, with the idea that we have a continuum. So the properties are not changing drastically from one point to another. And we have, let's say, the properties that are average properties because we have a huge number of molecules or, let's say, atoms and so on. So this means that, again, if we are thinking to nanoscale thermodynamics, we need to pay attention because depending on the pressure, for example, we have that. Just a moment. Is it working? Oh, okay, sorry. We may have very few molecules, okay, when the pressure is very low. And this means that we cannot use any more continuum models, okay? The strength of the thermodynamics, as you know, is that is a phenomenological theory, but then and is dealing with macroscopic phenomena. And is very, very good in the prediction of, in general prediction of processes, where we have, let's say, heat and work exchanges and so on. Sometimes it's a problem to use thermodynamics because we are trying usually to stretch thermodynamics too much. So we are saying, okay, this should be always in equilibrium, everything should be fine, but this is not the case. We were speaking about cavitation, where the non-equilibrium thermodynamics is really very important. So, okay. So you can still use the equilibrium thermodynamics, but pay attention if the phenomenon is very fast, it doesn't work anymore. For example, when you're working with a laser, let's say that I have very, very short pulses, and you're going to work, for example, a metal, to cut the metal and so on, it's not anymore a problem with equilibrium thermodynamics. You should include phenomena that are really linked to non-equilibrium thermodynamics. Okay, my approach in the classes is so-called semi-postulatory approach. So there are different approaches. Let's say when you are teaching thermodynamics. Okay, one way is to say, let's start with from the phenomena and somehow almost, let's say, looking at the history of the thermodynamics, you are building up the framework of classical thermodynamics. Another way is to say, okay, we have already known that the thermodynamics is a good theory, so let's postulate. Let's postulate properties, for example, for the entropy. And then we can say that if we are postulate these properties for the entropy, everything is working downstream. Okay, this is another way. I'm using the second way to teach thermodynamics because it's much faster. Otherwise, I took always a lot of time for the understanding of the phenomenon and so on before arriving at the entropy or internal energy. In this way, I can really, from the second day, I have all the tools to use the thermodynamics and to prove that it's working for many phenomena. Okay? So, and another point is that a thermodynamics system is called simple when the system is homogeneous isotropic. And it's another point that we tend to forget when we are doing advanced thermodynamics. Okay, one can think, well, why you're saying that? We know that. Yes, but pay attention that most likely when you're doing the thermodynamics in undergraduate courses, you are thinking to a simplified system, homogeneous, isotropic, but then there is no charge, so it's electrical neutral. There is no electromagnetic fields, no chemical reactions maybe, and no interfaces. When you have two simple systems together, there is a wall. No, we are saying there is a wall. But the wall for us is an interface, and the interface has some physics inside. So we are forgetting this, okay? But in fact, for a multi-phase system, this is very important. The interfaces are playing a big role, so we cannot forget this. Thermodynamics is not only limited to these simplified systems, okay? So we can add chemical reaction, of course, we can add electromagnetism, we can add electrical charges inside and so on. Many years ago, I think 20 years ago, I gave a course of complex thermodynamics where all these simplification were cancelled. So we said, let's put electromagnetic inside, let's put interface inside, and so on and so on. So this is a good point to say. Composite system is a system with a more simple system together, and an isolated system is a system where we don't have any energy interaction, work and heat. And between simple system we have a wall, and the definition of the wall is very important to understand the process that is happening. Okay? If the wall can move, we can reach a mechanical equilibrium because it's moving among the surfaces, among the systems. If the wall is diathermal, we have a thermal equilibrium because the thermal energy can pass through. And we have also walls that are osmotic, so they can allow one species from one system to another. Okay? A closed system is a system where we have an exchange of energy, but not mass. And the open system is a system where we have both mass and energy transfer, energy exchange with the surroundings. Every time that we are transporting mass, we are transporting energy. It's not possible to transport mass without transporting energy, of course. Okay? As you all know, we have the most important maybe parameter, variable in thermodynamics, the temperature, which is a statistical parameter. And the thermal equilibrium means that every time that we have a contact between one system and another, and we have a diathermal wall, at the end we are going to have the same temperature. If we have a first system in contact with one of the other two, only one, and it's in thermal equilibrium, the temperature is always the same for all the three systems. So it's a very well-known law. The internal energy is the energy inside the system. When you're thinking to the mechanical physics, you are thinking about a system that has kinetic energy, potential energy. But with the thermodynamics, we know that inside the system there is an energy linked to the molecular properties. Okay, so this means that when we are transferring energy, work or heat to the system, we are changing the internal energy, but for example, the work is also able to change kinetic energy and potential energy. So we can move something using work, okay? And so the point in the classical thermodynamics is also important to stress is that the time is not considered. Is considered only when we are doing the heat transfer. We saw the time, for example. No, when we are dealing with flows, we are going to see the time. But if we are going deep in classical thermodynamics, the time is not anymore there, because what we have are states. So there are, let's say, situations in the matter where we can measure exactly the thermodynamic properties. And we are saying that the system is in equilibrium so that we can describe the system in one state. something is happening, we can describe the system in the final state, and we can say what is happening between the initial state and the final state, independently of the time we took from one state to another, independently. So the time doesn't exist in this sense, okay? So this, the point is that when you're speaking about thermodynamic equilibrium, I'm spending few words now because it's very important for the multi-phase flows, okay? When we are speaking about thermodynamic equilibrium, we are speaking about something that we cannot prove. Because if you are proving it, you need to enter in the system. You need to interact in this, with the system. So you are changing something. So in fact, the fact that the system is in equilibrium is a kind of postulate. We are postulate the system in equilibrium, and we can recognize that the system at the initial position is in equilibrium like in the final position if the thermodynamics holds. Only there. Only afterwards. And if it's not working, I'm saying for the people that is working with both with experiments and numerics, in fact, because sometimes the thermodynamics doesn't work. So you're doing something, you are predicting something, and it's not working. Why? Because in between, or even at the initial point or the final point, we are not in equilibrium. Okay? So it's not true that we can use always the thermodynamics, because it's not possible, because it's not possible to define really the equilibrium. It's a posteriori. In fact, we could say a system, a thermodynamic system is an equilibrium when, if you don't interact, it should stay in that position forever. If you don't interact, let's see. If you want to check, I would like to see if this is a system now and the system in 1,000 years, but you need to enter. And if you enter, done. See you. Doesn't work anymore. Okay? So it's a little bit delicate. Okay? So it's a kind of things that we can assume as a postulate. Okay? Another point is that sometimes we are forgetting, the thermodynamic variables are defined only in equilibrium. If the system in equilibrium, we know pressure, temperature, everything. Okay? If the system is not in equilibrium, we can only approximate. We can only approximate. We don't know exactly what is happening. Especially when the system is very fast. I'm studying now, for example, flash atomization of hydrogen. The process is super fast. Okay? During the process, you don't know what is happening, really. So you know at some stage. But in between, you don't know. And then we are coming to the postulate that when you read this is enormous. Enormous. Pay attention. An equilibrium state of a system with R components, R chemical components, okay, is completely defined. Oh, look at the molecules. If you are looking at the molecules, we have 10 to power 26 molecules in the system and so on, okay? So one can think, looking at this big system with really a huge number of molecules, subsystems there, that one needs to know something about that, okay? Okay, maybe not 10 power to 26, but maybe 10 to power 9, maybe. Not bad, okay? No, we need less than 1 billion parameters. 10, no, 100, maybe 100, no. 10, no. R plus 2. When I'm thinking to that, every time my mind is exploding, because we have billions, we have a number that we can even imagine what is inside the system, and we need only, for example, when we have only one component, 3 parameters to completely define the thermodynamic of the system. 3. I mean, what? Yeah. Of course we know that. But if you think really about this point, is immense. So we need to know, for example, energy, volume, and the number of moles. If we know that, we know everything. So it's something like, imagine that in India there are 1.5 billion people right now, maybe more. Because I mean, the last census was in 2011. So after 14 years, you don't know how many Indians are now in this country. But let's say 1.5 billion, okay? So you have an identity card, or you have a way to say, I am number 900,000,255, so something like that, okay? So now the identity card of a system, a thermodynamic system, is given in fact by 3 numbers. It's not bad, like a comparison, okay? 3 for a monocomponent system. As you know, we have extensive variables, intensive variables. The extensive variables are depending on the mass of the system, the size of the system, for example, mass, volume, entropy, magnetic moment, and so on. The intensive variables are not depending on size, for example, pressure, temperature, chemical potential, and so on, okay? And what is important that in an equilibrium state, all the thermodynamic variables are depending on these R plus 2 variables. All of them. All of them. In a non-equilibrium state, one very important difference is that the properties are changing in time and space. We are saying that the equation of state is a kind of functional relationship that is putting together the state variable. The most famous one is the ideal gas, PV equal nRT. Okay? So if you're considering a PV T space, for example, we have that the equilibrium state is represented by 1 point, and the equation of state is represented by a surface. So something that is not new for you, but is important to say. We can create specific variables, so we can divide the extensive thermodynamic variable by the number of moles or the mass of the system, and we can build up specific variables. And they are depending only on 2 variables then. So for example, P is depending only on the specific volume and temperature when you're considering the specific variable, volume, let's say molar volume or mass, specific volume. So the thermodynamics is saying that the total energy of a system can be, let's say, the variation of the total energy of a system can be considered, let's say, as the variation of the system due to energy transfer. And when we have an isolated system, the energy is varying for because of 3 kind of mechanical energy. One is the work of the force field, gravity, for example, which is where the system is integrated, is embedded, okay? Another work is linked to the deformation of the system, can be volume, area, or length, okay? And the third work is about the dissipation. Pay attention. This is interesting because the dissipated work is linked to the viscosity, friction, okay? Any dissipative action. So we have a mechanical work in the sense that this work is going to increase the internal energy. And then this can produce the heat exchange, okay? So when you are, let's say, trying to scratch a surface, so you are doing work on the system, this is increasing the internal energy. The internal energy is increasing, so the temperature is increasing, then we have a heat. So we are converting the mechanical work in heat through the internal energy. Okay, so the dissipation is a kind of mechanical work that is going to be dissipated, can increase the delta U, and then can produce heat. But pay attention to this sequence, okay? Because sometimes we are saying, oh, dissipation, viscous dissipation is producing heat. Yes, but it's a consequence. It's a consequence. It's not directly. No, there is something in between. Okay? So, this is important to say because sometimes a little bit there is a confusion on that. Okay? So, in a system that is, but I would like to skip, otherwise I don't have time, sorry. So, the point is that when we have two systems in contact, so we don't have work, we may have a difference of the internal energy for one of the subsystems. And this is linked to the transfer of energy called heat. So in fact, if we are also including the heat, we have the first law of thermodynamics that in fact is a balance of energy. Okay? So it's saying that the variation of energy, of the total energy of a system, is equal to the work that is going to be an input of energy in terms of work, so mechanical energy, or we are going to see what is really work after, the slide after, and the heat. So the energy that is transferred because we have a difference of temperature. The heat is when we have a difference of temperature. I'm repeating this. Okay, this is a very important point. So, being a physicist, you see that I put an E that is the energy that is entering in the system. Okay, so it's positive when you are entering. It's something like a bank account. If you put energy inside, the bank account value is growing, right? So, all this, if so, you have a positive work, is going to increase the energy. If you have a positive heat, it's going to increase the energy. I'm saying that because there is another convention, conventional way is a Q minus W. You are going to have many tests with Q minus L because they are considering already the work output. Okay, this is very good when we are dealing with, for example, with engineering problem. But if you are looking at the physics, then this can create a confusion when we are dealing with, for example, Navier-Stokes equation with work and so on. But so I prefer this way to say. The other one is perfectly fine. I'm not saying that. It's only a question of convention. The work can be, for example, also let's say the mechanical work of having compression or expansion. And everybody knows here that we have that the work due to the variation of volume is minus P multiplied by the variation of the volume. Okay? I don't want now to enter in this. But pay attention that the work may contain other processes. For example, we may have the deformation work linked to the variation of the area, where we have sigma is the surface tension. So when we are going to have a problem where we have a difference in the area, we have a work done by the surface tension of the system. Or for example, we can have a spring. So we can have a difference in length, and this is again work linked to the elasticity coefficient. Okay? Not only, we could include also, for example, a magnetic field, magnetization, electric field, polarization. So in fact, the expression of the first principle of thermodynamics is not only the classical one, but you can include other terms if you have other phenomena to consider. We said that the thermodynamic variables, for example, for, let's say, a monocomponent system are depending on the other, let's say, other two parameters, for example, U and V, or generically with the two other, let's say, thermodynamic properties. So we can always write, for example, a property, in this case the specific volume, as a function of temperature and pressure. So we can write a question like that. And in general, we can write an expression, let's say, of this kind when we would like to understand one parameter can be written with something that we know. We can measure something. Okay? So, for example, we would like to have the coefficient of volume expansion that is 1 over the specific volume, the V specific volume over the T at constant pressure. So, well, not bad. So it's an isobaric coefficient. and we would like to measure, we can measure it, okay? The same for the compressibility. So we can think to experiments where we have an isothermal process, and we can measure the variation of the density, the specific volume, the density. So we can think to measure, we can think to measurement techniques to have at the end the properties of beta and K depending on pressure and temperature, because also beta and K are depending on pressure and temperature, of course, okay? And so we can put the things together in order to have at the end the variation of all the thermodynamic variables in a given range of pressure and temperature. And we can notice, for example, that our variables that are not depending too much on pressure or not too much on temperature. Temperature is more difficult. Every time we have the temperature is always characterizing the variables. But the pressure, well, for example, the thermal conductivity is not depending on the pressure, on a very, very wide range. Okay. Another point that is interesting is that the thermodynamic properties are very smooth. The function describing these properties is very smooth. So in this case, we can write the second mixed derivatives so of this function divided by the x and y is equal to the same, but first of all, we are derivating with x, and the second one with epsilon. So we can say that we can build a relationship like this one, so that the partial derivative with respect to the temperature of the partial derivative of the entropy with respect to the volume is the same, is equal to the partial derivative of with respect to the volume of the entropy derivative with respect to the temperature. So we can write this expression, and this is very important. Yeah? And this is very important because we can have all the possible combinations among variables using this kind of principle. So another point is that the first principle of thermodynamics we can write now only for the internal energy is that the variation of the internal energy is equal to the heat exchange and work exchange. Okay? So if we are thinking in terms of the differential, we can say that the U is equal to a differentiation of the Q and the differentiation value for the work. But this doesn't work. As you know, when you have a state variable, you can do it, so you can differentiate it, you can integrate, because you know the equilibrium value at the initial point and the final value and the value at the final state. So, okay. So, and then this is independently how the system went from the initial position, initial state, to the final state. Okay? So if you have this is, for example, this is working very fine with a bottle like that. We have a given energy here and a given energy here that is higher because we have the difference is how much? Is 1 meter, something like that, 1 meter 20 centimeters. So we know that the variation is mgh. Okay? But this is independent on the fact that I throw this bottle in the class. I'm doing this with my students. I'm throwing the bottles, then give me back. And now, how much is the energy variation? Well, it's the same. It's the same. So this is happening also for the internal energy. So the other two variables, in fact, they are not state variable, but they are process variables. So they are depending on the process. This means that we cannot write them in terms of an integral because we must know how the process was done. Okay? So they are, in fact, they are inexact differential. Everything that you already know, so I would like really to be fast here. And if you want to integral, to make an integral of a process, for example, you have that okay. So we saw that the work is we can write the work in terms of pressure and volume. So pressure multiplied by the volume, the variation of the volume, we can integrate PDV between initial state and final state. This is possible, okay? But this doesn't mean, of course, that we are writing something like that VE is equal to an integral between E and V of the dVA. Okay, this is not possible, because again, it doesn't exist a work at the initial state and a work at the final state, or it doesn't exist a Q at the initial state and the final state, but we need to consider a process. Also in this case, when we are writing an expression like this one, still we don't know if it's possible to integrate, because we can integrate only if these two variables are known along the process. And so, since many times it's not so easy, we are considering an ideal process that is so-called quasi-static. Pay attention that quasi-static is a very false word. It doesn't mean anything, quasi-static. What does it mean, quasi-static? Okay. But for us, the quasi-static process is a traditional way to say that during the process, you know at each time, in each moment, in each position, you know pressure and volume. So you know the value of the properties, okay? When the process is non-quasi-static, you know only the endpoints, the initial and the final points, okay? There is sometimes in physics, but also in engineering, we're using the word reversible, okay? Reversible, this time the word that makes sense, means that we can go in one direction with a small change, and in principle we can come back, okay? So we can go back to the initial state. So in fact, the reversible process is a quasi-static process. For example, there is no dissipative forces, because every time that you are doing something with dissipative forces, then you are losing this chance to be reversible, okay? Because you are going in one direction, and we are going to see that we are increasing the entropy, and we are increasing again the entropy coming back. So, doesn't work, okay? So we are not coming back really in the same position. We change one of the variables, very important one, okay? So, doesn't work. So, a reversible change must be quasi-static, so we need to know all the variables, but pay attention that the quasi-static process can be irreversible. So the two words are not the same, even if many times we are using like, oh, it's a quasi-static reversible. No. Doesn't work like that, okay? So a quasi-static process, so a process where you know all the variables, can be reversible. For example, in case of the hysteresis, when you're doing this process, you're not coming back, okay, to the same point. But you know the properties. So you know the properties, so it's a quasi-static process, but it's irreversible, okay? But if the process is reversible, it's quasi-static. Okay, so I think that I will give you these slides. What is the sun giving to us? What do we have at the end? At the end? Heat? Well, if the sun is giving us heat, in let's say a net energy coming from the sun, we are going to die, everybody. In fact, what we are receiving from the sun, we are giving back, not to the sun, but to the universe. Otherwise, we have a problem. So otherwise, we are going to heat up the earth. So the sun is giving us energy, and we are spreading energy. Pay attention, the same amount of energy into the universe. So it's not really the net contribution is not the energy. Otherwise, we have a problem again. If the net contribution of the sun to us will be the energy, we are going to be 1,000 Kelvin very easily. It's not a problem. It's not possible. No. What is giving us? We can even calculate. The energy is coming to us. Outside, what we have, 1,353 watt meter square. So every square meter, we have 1,353 watt. is a lot, that is coming to us. The Earth is receiving this quantity of energy, and they're dissipating like a black body at 4 Kelvin, at 4 centigrades. So 277 Kelvin. Okay? So we are like a body that is receiving energy and then is spreading energy. Okay? Good. Thank you, Sun. But we are receiving the money and we are giving the money away. Okay? So no, we are receiving something else. We are receiving energy, but with a lower entropy. Is the grade, is the quality of energy that we are receiving. That is very important. Not the quantity. It's the quality of the energy. The quantity is not important because we are giving away. But is the quality in the sense that is giving high temperature energy. And we are distributing the energy everywhere, which is a low grade energy. Okay? Think about that. Okay? I'm teaching this to the students. The students say, what? Yeah? No, because why I'm saying that? Because we need to introduce entropy. Okay? Without the concept of entropy, it's difficult to understand. We are receiving energy, we are giving back energy. Well, yeah, nice. Thank you. But how is it possible to have life on this planet and so on? Okay? In fact, we need to consider the entropy. And the first thing is the entropy postulate. So, it exists, and also this is something, wow. It exists a function called entropy of the extensive parameters U, V, and N, because we know that the equilibrium state is defined by R plus 2 parameters, so U, M, V, and N, okay? For any composite system, okay, that is always defined for the equilibrium states and have as a property, having a property. The value assumed by the extensive parameters are those that maximize the entropy over the manifold equilibrium states. So, this is immense again. So we have one variable that tends to, let's say, to grow, tends to grow for a system. When we have an isolated system, this variable, we don't know what it is now, because this is a postulate, but this is a function of the parameters, that if the parameters are varying, every time they are varying, the entropy is growing in the system, which is a bit strange, because we know that we have functions that are going to change. If you are changing a parameter, then maybe the variable is going down. Okay? No. When we are, let's say, in equilibrium states, a given set of variables, and this function is maximized by any set of variables in equilibrium conditions. And the other point is that the entropy can be written in this way. This is only a way to write the entropy, but it's a good way. So it's a way where we can see that we have internal energy, temperature, pressure, volume, and chemical potential and number of moles, because we said that the entropy depends on R plus 2 variables. Okay? We can write a definition of entropy, including the generalized work, because consider that here we have also pressure and volume, but if we are considering, for example, magnetism, we need to include the magnetic field and so on. So we can have a more complex version of the entropy. This is an interesting point. Okay? So, again, I don't have time. I have only a few minutes. But what is important is that the entropy is an extensive properties. So, for a composite system, is additive. Okay? And the entropy function is continuous and differentiable, and is monotonically increasing function of the energy. what is saying the second principle of thermodynamics is saying that if a system is thermally insulated at a constant volume, so there is no exchange, it's completely isolated, okay? The variation entropy inside this composite system may have only 3 results. And in fact, in reality, there is only one. So we have an increase of entropy for any process inside of an isolated system. So the first law of thermodynamics is giving us an energy balance. The second law of thermodynamics is giving a direction of the processes, in which direction they are going. I think, again, everything that you should know, we are going to have for the people that came later, we are going to have a warm-up this morning, and then because tomorrow we are going to have multi-phase flows, but it was a kind of bridging lesson, so we are going to have 3 hours of repetition of concepts that maybe everybody knows. But, for example, the fact of the sun, maybe you didn't think about that. Maybe, I don't know. Even if you are in the sector, maybe you are not thinking to these points, sometimes. So it can be very interesting. And then, for example, the entropy of the universe is conserved. The point is very interesting, this point, because there are a lot of works on the fact that maybe we have a situation where we have the entropy that maybe is decreasing in some situation and decreasing in other, let's say, zone of the universe. The theory here are very interesting and so on. But it's very clear that inside the universe there are only 2 variables that are growing, which are entropy and time. And in fact, they are connected, completely connected. Okay? The time is something unreal. Entropy is more real than time. We are trying to consider time very real because we are looking at the cycling processes that we have around, the sunrise, sunset, everything. So we'll build up, let's say, a cultural, let's say, way, a social accepted form to say that we are in a time situation. So because we see the people, our relatives, ourselves, we see the things that are changing in time. And then on this time that we created, looking at the cycles, and then there was a guy, not stupid, honestly, Newton, and he started to do a mathematics in physics, looking at putting one parameter that was the time, the t, famous t. Everywhere now we are dealing with a t when we are dealing with mechanics and so on. So and this was very useful, in fact. It's very useful. But what is inside time is really more connected to entropy than time itself. So if you're looking really deep in statistical physics, for example, you may raise problems with the nature of time. So I need to be fast. This is the fundamental equation in differential form. And what is interesting is that inside the entropy, when you know the entropy, the form of the function entropy, you know everything of a system. In fact, for example, we are doing simulation of stochastic hydrodynamics with fluctuations, putting inside a given, say, material, because we know the form of the entropy. So we know the fundamental relation of entropy. And if we have the entropy, the function, we know everything. We know Cp, we know K, we know beta, we know the everything, density, everything. So if we know the entropy, we know all the equilibrium states of the system. And as you know, we can write the Gibbs-Duhem equation, and this is very important for the phase change. Let me skip this, because otherwise it's not possible to continue. If we know the entropy, we can write the entropy function, we can write the internal energy in terms of entropy and, in this case, volume, because we are considering only the work linked to the deformation. The mechanical work here in this expression is not only in P dV. Do you remember what I wrote? The work was made by three terms. The work of the field, the work due to the formation of the system, and the work due to dissipation. Okay? And one can think you are not considering the field work, and you're linked to the potential forces, the potential field, and you're not considering the work linked to the dissipation. No, it's not true. In this expression, we have the work linked to the friction. And this here is inside the S. So it's very interesting. So the entropy, in fact, is changing with the heat and the friction and the dissipative process. It's the sum of the two contributions, not only one. Okay? But in some way, it's giving us the chance to have a differential form to the heat. So TdS, in fact, is something linked to the heat. The heat was not differentiable, so you cannot write, but we can write now an integral like we did for the work for the heat. So we can write the heat is equal to minus integral of TdS. For example, if you are considering also the generalized work, like for example magnetic field and so on, the variation of the internal energy is becoming this one. See that it's enough to add the integral of the works. So in principle, when you want to understand something more about complex systems, you can do it with the equilibrium thermodynamics. Sometimes you are not thinking to the power of thermodynamics in this sense. We can have inside chemistry, we can have inside magnetism, electromagnetism, electrical charges, and so on. I will skip this one. Only to remind you the form of the Gibbs free energy. Okay? This is the finite form of the Gibbs energy, U plus Ts minus PV. U plus PV minus Ts, sorry for that. And then so we can write let's say the different forms. Again, we can add, if we have, let's say, other generalized work, you see that we can add this term in the expression to consider, for example, the interfaces. The interfaces are very important for multiphase flows. Imagine to have a bubble. When you have a bubble or you have a droplet, well, you have a variation of the work due to sigma, to the surface tension effects. So because you have, for example, a bubble is growing, so we have more area, so of course we have a work there. We need to include it. You cannot forget. This can be very important. The surface energy for many systems can be very important. When we have cavitation, surface energy is very important. And what is very interesting is that, as we saw from the Euler formula, we can put together, using the second derivatives of the functions, the different thermodynamic potentials. So we can write the potential using different expressions. And in this case, we can land with the fact that G is in fact the Gibbs, the free energy is in fact the sum of the chemical potential multiplied by the moles. We don't need this. And what is important is that, for example, the Gibbs energy is not going to reach a maximum like the entropy, but it's going to reach a minimum when we have different processes. So instead, the entropy is going to grow. The Gibbs energy is going to be lower and lower and lower for the different kind of processes. For example, chemical reaction. Maxwell equations are very important because we can write a different expression of temperature, volume, pressure, and so on. I will give you this PDF, so this afternoon you can go home or you're in the hostel or where you are, and you can see this part. Again, I don't have time now. What is important is that, for example, I would like to understand how much is the variation of entropy? Everybody is writing always that the variation of the variation of entropy, for example, for a gas, is a very classical, and then there is a mass here. MCP variation of temperature is very classical, right? Well, but the entropy can depend on the pressure, and we will see that this is important. Okay, so what is happening when we have also variation of the entropy with pressure? That we need to try to understand what is the value of this expression now. So we are starting with a differential form, and we are saying, oh, the entropy has two partial derivatives now, not only one. Okay, this is the classical form that they're using in the undergraduate courses, right? But then if you have, let's say, the variation of the pressure, then you have this term, but then you have something else. Where is this term coming? Oh, well, we can start with the differential expression for the enthalpy, and we can write that dH over dP at a constant temperature is equal to T multiplied by the derivatives of the entropy with respect to the pressure at the constant temperature plus V, of course. You are dividing by the P. Okay, fine. Now, from the Maxwell relation, you are going to see the Maxwell relation, let's say, in the previous slides. Not now because I don't have time. ds over dP with the given constant temperature, in fact, is equal to minus the V over the T at constant pressure. Okay? And so, if you are going to use this expression, you are landing with the, let's say, with this formula, which can be very important for multiphase flows. Because in multiphase flows, the entropy may depend strongly on the pressure. So, this is not valid anymore. Okay? So the Maxwell equations are very useful when you are dealing with different variables, when you want to have different conditions. A last point is that we are always speaking about real gases in the sense that inside the multiphase flow, inside the multiphase system, the gas may be not ideal. It's a real gas. Okay? So in this case, you need to think that the molecules and atoms, they don't have, let's say, there are not only more points, but they have a finite size. Okay? And the molecules are interacting with each other. In an ideal gas, they are not interacting. They are like particles going around chaotically, but with no interaction. So in fact, if you're considering this, you have that there is in the molecular interaction, for example, as a minimum. So here is a kind of a potential of the forces, and you have a repulsive force, because if you have, for example, if you're going in this direction, and the distance between the molecules is going to be very, very small, you have a very strong repulsive force. So you cannot put the two molecules together when they are very close. On the other side, we have also an attraction force. So the attraction force and the repulsive force far from the molecules is plus minus the same, so in fact they are in equilibrium. They are staying. As soon as they are being closer, they are not going to be pretty much closer because the repulsive force, but there can be an attraction at the given point. Okay? So this is the principle of the molecular interaction. So in fact, what is happening is that when you have high pressure, the molecules are close enough to be affected by this interaction. Okay? Also, when we have a low temperature, the molecules are low kinetic energy. And so they are, let's say, they are interacting easily. Okay? So what is happening is that when we are dealing, for example, with multiphase flows at high pressure, which is quite normal, okay? We have, for example, when we are dealing with gas and liquid in a nozzle, where we have very high pressure, well, this interaction is very important. So it's not anymore, we don't have anymore an ideal gas, okay? Someone of you asked me about the properties when we're having cavitation, evaporation, boiling, and so on. It's possible, for example, to use constant properties. So the properties are constant during a simulation for multi-phase flows. Yes, not always. Not always. Why? Because, let's say, for example, it's very important to have real gases inside the simulation of cavitation, not ideal gases, because the pressure can be very low or very high, or we have different temperatures. So it depends. What is happening is that, in fact, when we consider, let's say, the temperature, if you are going down with temperature, we don't have the classical PV over equal to 1 RT, but we have a variation. And this variation can be expressed by the van der Waals equations. So van der Waals is the scientist that during his PhD, he wrote this equation during the PhD, which is not bad. Mono. And this is something that was astonishing, beautiful, in the sense that it's something in the physics. Sometimes in physics there's something simple, and you wonder how you were able to think about this kind of stuff like that. So, and this is one of the equations that is simple enough, but is very powerful. It's still very powerful. And this linked to the fact that starting from the ideal gas equation, at short distances, the access, the volume that is accessible to the gas is not anymore V, but it's a little bit less, because if the molecules have a size, of course you cannot put the molecules together. Okay? So in fact, if you consider the n molecules inside with a given size, you have the volume is not anymore V, but V minus NB. On the other side, as I told you before, the collision frequency is changing because the pressure, is changing with the collision frequency and the force of the impact. So in fact, there is a decrease of the pressure due to the fact that we have closer and closer molecules, no? And he wrote A multiplied by N divided by V squared, okay, to consider the variation of the pressure due to the collision, no? When we have high pressure. So, which is interesting, I'd say, no? And then he landed with this equation that is a good equation for real gases. This equation has a point. You can see here that if you are, say, drawing the pressure against the molar volume, you obtain this curve, and here we are going to have the classical PV equal RT. Okay? But down we have this kind of situation where you see that we have a minimum. We are reaching a minimum at the given point. It's important in the next discussion, so remind this point. Okay, I don't have time now for this. There is a constructivity factor that is saying how far we are from the ideal gas condition. Okay? So at low temperature, the deviation is quite big. But also, let's say when we are dealing with very high temperature and so on, this value can change a lot. Okay, so the ideal gas is working, but in a very small range of temperature and pressure. Okay, I don't have time for this. And I think that in this way I finished. Okay,